Yeah, the title of the lecture is Climate Change Impact on Hydrology and Hydro-climatic Extremes, Evidences from the Modeling Studies. The main objective of this lecture is to introduce what are the approaches available for the climate change impact assessment on hydrology and water resources. And also, I will try to introduce the modeling framework to assess the climate change impact assessment on hydrology and water resources through a few case studies that myself and some of my students they have conducted in master's and PhD thesis and some of my project works. So this is the outline of my lecture today. You can see that I will be explaining brief on the hydrological cycle or water cycle. What is the pathway of climate change impact on hydrology and hydrological cycle? Then I will briefly describe about what are the approaches available for climate change impact assessment on hydrology and water resources. I will also explain about the modeling framework for climate change impact assessment on hydrology and water resources. And probably all the participants would also be benefited from the explanation of what are the data and tools required for climate change impact assessment on hydrology and water resources. And I will finally present the two case studies. One is climate change impact assessment on hydrology of one of the river basins in Nepal called Marsandi River Basin. And the another case study is on climate change impact on the hydro-climatic extremes under climate change in Burigandagi River Basin of Nepal, Songkram River Basin of Thailand, and Upper Sitaram River Basin of Indonesia. Probably I will stop after some of the contents to have more discussion session. Okay, so let me briefly explain about the hydrological cycle or water cycle, because it is very important to understand what is the meaning of the hydrological cycle or water cycle, because the climate change impact on water resources is basically from the impact on the hydrological cycle. So as I mentioned you that it's very important to understand about the hydrological cycle or water cycle to understand how the climate change impacts the hydrology and water resources of any watershed or any basins or any area. So the hydrological cycle is also called as water cycle, and it describes the continuous movement of water in our earth. And the water changes its states in the hydrological cycle. For example, water change its state from liquid state to vapor state, and also the vapor state to liquid state. Similarly, from liquid state to the solid states in the hydrological cycle. So it means that the water moves from one storage to another storage through various hydrological processes, and these processes are, for example, the evaporation, condensation, the precipitation, the surface runoff, infiltration, groundwater, and finally it goes to the ocean, and the cycle repeats continuously. So the availability and the quality of water in any location depends on the hydrological cycle of that hydrological unit. There are two key factors that drives the hydrological cycle or water cycle in our earth. So over the ocean, the surface temperature is a major controlling factor which drives all hydrological processes, and the surface temperature over the ocean varies very slowly. Over the land, there are two effects that drives the hydrological cycle or water cycle. One is the surface temperature, and the other one is the available soil moisture. And unlike the over ocean, the surface temperature and available soil moisture may change relatively quickly compared to the over the ocean. Basically, there are two factors affecting the hydrological cycle or water cycle, and they are natural factors and man-made factors. So the natural factors include the climate, topography, vegetation, and soil type. And the man-made factors which affects the hydrological cycle are deforestation and afforestation, construction of the buildings, construction of the reservoir, land use and land cover change such as urbanization. So since the topic of this presentation is more on climate change impact on the hydrology and water resources, I'll be talking more on how the climate change impact the hydrology and water resources of a given river basin or watershed. So before that, I want to explain a little bit on what is the pathway of climate change impact on the hydrological cycle or water cycle. So all of you know that there is increase in the greenhouse gas emission, and with the increase in the greenhouse gas emission, there is increased concentration of the greenhouse gases in the atmosphere, such as carbon dioxide, nitrous oxide, sulfur dioxide, and so on. And because of the increase in this kind of concentration of the greenhouse gases, there is increased in the radiative forcing of the earth, which is also called the global warming. And because of this global warming, there is heating of the atmosphere and also the increase in the surface latent heating. And because of this process, there is increase in the temperature of the atmosphere. And because of the increase in the temperature, there is also increase in the evaporation from the ocean, land surface, and also the vegetation. So there is a physics behind the temperature change, and then also the atmospheric water holding capacity. So if there is an increase in the temperature of the atmosphere, it also increases the atmospheric water holding capacity. And with the increase in the evaporation, there is also increase in the atmospheric moisture content. So higher the temperature of the atmosphere, higher the moisture holding capacity of the atmosphere. And all of you know that atmosphere cannot hold more water for more than 5 or 6 days. Then it has to discharge water either over the ocean or land surface and vegetation. So it means that with the increase in the temperature of the atmosphere, the hydrological cycle, speed up is occurring, and that will enhance the precipitation rate. Again, there is more moisture available in the atmosphere, and again, this process continuously happens, and that will also influence the hydrology or water resources of any given location. So as I mentioned that climate change impact the hydrology and water resources of any given location. It can be watershed, it can be a river basin, and so on. So there are basically two approaches available to conduct climate change impact assessment on the hydrology and water resources. And these two approaches, one of the approaches is called top-down approach, and the second approach is called the bottom-up approach. So in the top-down approach, this is basically desktop study where different type of emission scenario will be constructed, and then those emission scenarios will be fed into the climate models, basically general circulation models or global climate models, and from there we construct the future climate scenarios, and these future climate scenarios are fed into the hydrological model or any other water resources systems model to assess the impact of climate change on hydrology and water resources. So this is a approach called a top-down approach in the climate change impact assessment on the hydrology and water resources. On the other hand, there is another approach called bottom-up approach, and this bottom-up approach is basically participatory approach where we try to find out what are the risks to the water resources systems, and we try to take the informations given by or available in the particular area, then use those information to assess the climate change impact on the hydrology and water resources. Unlike the top-down approach, this bottom-up approach is widely used by the communities which are conducting the climate change vulnerability assessment or climate change adaptation assessment. So in this study, I will focus more on the top-down approaches for climate change impact assessment on the hydrology and water resources. Okay, so this is the general modeling, the framework for climate. Actually, this is a two-step process. In the first step, we generate the climate change scenario. Okay, Professor Ajay, can you hear me?
Yes, now it's clear.
Okay, I think my internet connection is not stable, so if you can hear me, that's fine.
Yes, it's fine.
Okay, so the modeling assessment framework here is a two-step process. In the first step, we construct the future climate scenarios, or in other words, we try to forecast, or we try to project how the climate will change in the future. For example, how the temperature will change, how the rainfall will change, and how the other climatic parameters will change in the future. Because this future climate is necessary to assess the climate change impact on the hydrology and water resources. So in the first step, we construct, we project, or we create the future climate scenarios. So there are several techniques to create the future climate scenarios, and one of the techniques is use the data of the general circulation model or regional climate models, because these are the main source of the future climate data. So these climate models have future climate data up to 2100, 2200, even 2300. Okay. So but the climate data from the general circulation models or regional climate models, they cannot be used directly to assess the climate change impact on the hydrology or water resources at the local scale or the basin scale. So what we need to do is we need to translate the data or climate data of the general circulation model, GCMs, or regional climate models into the local scale by a process called downscaling or bias correction, because the general circulation models or regional climate models, they usually projects the climate data at the very bigger scale, and also the course resolution. But the impact assessment studies are mainly conducted in the local level, right? So for example, watershed level, or for example, basin level. So these climate data should be translated into the local level, and we can use the process called downscaling or bias correction. And there are several techniques of the downscaling and bias correction. So depending on the availability of the data, depending on the skills of the researcher, we can use any of the method to downscale the climate data of the general circulation model or regional climate models to the local level. So once we have the future climate data, the second step consists of using this future climate data to the hydrological models to predict what could be the hydrologic conditions under the future climatic conditions. So there are several hydrological models or hydrological tools available for the hydrological modeling, right? So, but before we use the hydrological models, we have to, calibrate or validate these hydrological models to see whether they are really capturing the hydrological processes of the given watershed or the given river basin to simulate the climate change impact on the hydrology and water resources. So this is the general, modeling framework to assess the climate change impact on the hydrology. So to summarize, assessment of climate change impact on the hydrology is a two-step process. In the first step, we generate or we construct the future climate scenario of that location, and we use that future climate data and feed into the hydrological models, and we generate the hydrological conditions on the future climatic conditions. Since the faculty development program is itself water resources systems modeling, I think there will be several lectures on the hydrological models or hydrological modeling. But I just want to define the meaning of the hydrological modeling here. So the hydrological modeling is defined as characterization of the real hydrological features or the system by the use of small-scale physical models, mathematical language, and computer simulation. So the hydrological modeling is a creation of the artificial representation of the real world system. Here the real world system is the hydrological processes of the watershed or hydrological processes of the river basin, and that artificial representation of the hydrological processes is represented by several numerical equations. And once we provide the input into those the artificial representation of the hydrological processes, we can get also output from that the artificial the hydrological systems in terms of the several hydrological variables such as runoff, groundwater flow, and so on. So we use several kinds of the hydrological models to simulate the hydrological processes under the changed climatic conditions. There are different kinds of the data required for the hydrological modeling or climate change impact assessment on the hydrology and water resources. Some of the data I have outlined here. We need the basin characteristics or the watershed characteristics, such as topography of that location, soil type of that location, land use and land cover of that location, And if there exists the water storage or water diversion, we also need those kind of the data. And these data are very essential because it affects the the hydrological processes of the given watershed or given basin. We also need the observed climate and river discharge, and these includes the rainfall, temperature, river discharge. So in the climate change impact assessment studies, we usually require the longer term data of these climate and river discharge. The minimum data requirement is of at least 30 years. And we also need the future climate data, and then these future climate data we generally obtain from the general circulation model or the regional climate models, and these are the very reliable source of the future climate data. And there are several modeling centers, or there are several climate change research centers, and they usually provide these data free of cost. So these data can be freely downloaded from those kind of centers or the research centers website. And one of the link I have given here where we can find the climate data of at least 100 years from several general circulation models or regional climate models. And it's always good to use the national data set, but many of the times these data are not available from the respective government agencies, right? So in our region, there is always scarcity of data. So there are some alternate sources of the data, and these alternate sources of the data I have also outlined here. For example, for the digital elevation model, which is the topography of the given location, can be downloaded from the website of the USGS or the NASA. So they have a different resolution of the DEM available. For example, from the USGS, the digital elevation model of 90-meter resolution is available. From NASA, the digital elevation model of 30-meter resolution is available. Okay. The soil data, there are different center or different website available for the soil data also. Recently, very high resolution soil data is available from this International Soil Reference and Information Center, which is of 250-meter resolution. But there are other websites where you can also download the soil data, for example, Food and Agriculture Organization of the United Nations. But those are coarse resolution of the soil data. Similarly, land use and land cover data, they are also available from several, the website and also from the projects. For example, the annual land use and land cover data is available from European Space Agency, ESA. And the duration of the land use and land cover data is from 1992 to 2018. So this is annual land use and land cover data available. Similarly, temperature and precipitation data are also publicly available. For example, this is one of the project called Aphrodite, where the temperature and precipitation data from 1951 to 2015 is also available. And these data are at the daily resolution. So these are some of the list of the alternate sources of the data if we do not have the data from the respective government agencies. Okay, so for the impact assessment, there are several tools or models available, and these tools or models are either hydraulic models or hydrology models or planning models. So depending on the purpose of the climate change impact assessment, we can use either of these kind of models. We can use either hydraulic models if we are interested to assess the impact of climate change on floods, right? But if we are interested in climate change impact assessment on the water balance or hydrological or rainfall runoff processes, then we can use the hydrological models. Similarly, there are models called water resources systems model, and these water resources systems models can be used to see how we can allocate the water resources for different beneficial sectors, or how do we optimize the water resources allocation to different beneficial sectors. So in that case, we can use these water resources systems models. Okay, so there are several models available to conduct the climate change impact assessment on the hydrology and water resources, and the selection of the models depends on the purpose of the climate change impact assessment. So these are some of the names of these different types of the models. For example, there are the operational and hydraulic models, such as the HEC series. Hydrologic Engineering Center developed these HEC HMS, HEC-RAS, and HEC-RACIM. So I have given you here what is the web link to download those models. Similarly, there are models called Waterware, Riverware, Mike 11, and Delft 3D. So some of the models are freely available. We don't need to pay, but some of the models we have to pay to access the license. These are the planning and hydrology models, such as water evaluation and planning model, which is also called WIP model, developed by the Stockholm Environment Institute. Soil and water assessment tool, this is developed by the USDA. I think in this faculty development program, you will be learning about the SWOT model and how to use the SWOT model. There are some other models, such as interactive river and aquifer simulation, river basin planning and management, Mike 21, and Mike basin. And again, some of the models are freely available to use, but some of the models we have to pay to use models. Okay, so I think I will stop here for a few minutes for question and answer session. So if you have any questions related to the contents I have covered until now, I'll be very happy to discuss. So Professor Ajay,
Yes.
probably participants would be interested to ask some questions.
We had requested the participant to raise the question in the chat box.
Mm-hmm.
And so far, I see only that one question from Sunny Agrawal, and he is asking that how to validate future climate scenarios. How to validate future climate scenarios?
Yeah, that's very important question, Professor Ajay. Okay, so we are talking about the future, right? So and there are a lot of uncertainties related to the projection of the future climate. Okay, so what we have to do is we have to use these climate models to project the future climate scenarios or future climate, right? So there is a process called evaluation of these climate models. We have the historical climate data, and then these climate models can also simulate the historical climate data. So once the historical climate data is simulated by the climate models, we can compare the historical observed climate data. And if the climate model simulated historical climate data and the historical observed data is quite similar, then we believe that the model which simulate the historical climate data accurately will also simulate the future climate data accurately. So that's the assumptions we have to make. Okay. So there are no other ways to validate the future climate data, because this is happening in the future time period, right? So we have many general we just compare the historical climate data and the historical climate data simulated by the climate models, and if they have very good correlation, we assume that these models works well in the future to project the future climate data. Is that clear?
Yes, yes. I think, Sunny, that this should be clear to you. Historical climate data need to be predicted by the climate models, and then we can see how this is close to the observed value. I think that's good. We have 2-3 more question. Savita NM, and he or she is asking, what should be the minimum length of meteorological data needed for climate modeling? What will be the minimum length of meteorological data needed for climate modeling?
Right. This is also a very important question. Normally, we require at least of 30 years of climate data. Okay. So the World Meteorological Organization, they recommend use of the 30 years or more than 30 years of the meteorological data to define the climate of any given location, right? So it means that if we want to study the climate change or climate change impact assessment studies, we need at least 30 years of the climate data.
Thank you so much. Yes, one more question is there from Tausif Ahmed, and he's asking that what are the hydrological models used to analyze the impact of climate change on the urban areas?
Okay.
What are the hydrological models used to analyze the impact of climate change on the urban areas?
Okay, that's very good question also. As I mentioned that, there are several types of the models which can simulate the hydrological processes of the watershed or river basin, also the urban area, right? So we need the models which captures the hydrological processes in the urban area. And there are several, urban hydrological models which can be used to assess the impact of climate change on hydrology on urban hydrological processes. So one of the very popular models available is called PC-SWIM. This PC-SWIM model can be used to assess the climate change impact on the urban runoff or urban drainage. And again, there are several other hydrological models available to predict the climate change impact on the urban hydrology. So these are basically urban hydrological models like PC-SWIM or the basin model. Thank you.
Yes, PC-SWIM means SWMA model.
Yeah, right.
Yeah. Okay. Mr. Suman Dev Burban, and he is asking that what may be the impact of climate change on sediment load of a river basin. Climate change impact on sediment load of a river basin.
Yeah, that's also a very good question. And yeah, it depends on how the climate will change in that river basin. And how that will impact the the runoff processes in the river basin, because they are linked, right? So, for example, if any river basin the rainfall is projected to be very low, then probably that will generate either no sediment or soil erosion, or very less soil erosion, right? So in that case, probably sediment load will be very less. But if the rainfall intensity is very high, and depending on the land use and land cover, soil type, probably there will need to we really need to conduct this climate change impact assessment on the sediment yield or sediment load also.
Yeah, actually, under climate change impact, lots of accumulated rainfall can occur in a single day. So this is what this has been predicted.
Right.
So more rainfall means a more generation of runoff.
Right.
So more generation of runoff can be understood to give more sediment yield, which will finally go to the river basin if you are not managing your land uses.
Exactly. Yeah, so, that's right. Yeah.
Yeah. In the first class, I have requested to all the participants that before you do the modeling work, you please read the hydrology very well. You must understand that what are the factors which are going to affect these hydrological processes. So they can understand the modeling processes.
That's correct.
We will take one more question, then you can continue the lecture. Yes, Vanita Pandey, she is asking, can be stochastic modeling also be used for similar accuracy of future hydrological modeling of climate change assessment? We can use stochastic modeling for similar accuracy for future hydrological modeling of climate change assessment?
Right, that's also a very important question, Professor Ajay. So there are several types of the models we can use for the climate change impact assessment on hydrology, water resources, right? So yeah, I cannot say, definitely stochastic models are having similar performance with the other kind of, deterministic or, other kind of models, but these models can also be used. But again, we have to compare the performance of these models. But definitely, stochastic models can also be used to assess the impact of the climate change on the hydrology. Yeah.
Yeah. So, okay, we will take remaining question later.
Yeah, I think
there are. Please continue.
Yeah, there are several very important questions I saw in the chat box.
Okay. And now you can respond. You can respond.
So we have the question and answer session also. I plan to keep it, after every the major contents I covered. But anyway, yes. I think there is one question by Sumandev Burman. I see presently in different river basins, several dams, barrages constructed. So how to assess climate change impact on river discharge? And I think this is very, very important question. Yeah, the hydrological processes are impacted by not only the climate change, but also the anthropogenic factors, right? For example, construction of these barrages, reservoirs, water diversion, land use and land cover change. We convert the forest land use to agricultural land use, forest land use to residential land use, and these will have all impact on the hydrological processes. So in this case, we have to assess the combined impact of all these factors on the hydrology and water resources. it's not only the climate change that impacts the hydrology and water resources, but it is also other factors. So we can do several, simulations or scenario analysis. For example, if there is only change in the climate in that basin, what will happen to the hydrology? Okay, and if there is change in the climate, maybe there are some other changes also, right? So the construction of the barrage, construction of the reservoir, land use change from the forest to urban area. So we need to assess the individual as well as the combined impact of those changes on the hydrology. Okay, so I still see there are many questions. So I will, describe some of the case studies, and then we can come back.
Yes.
Is that okay?
Later we can discuss it.
Okay.
So you please continue.
Okay, so I will explain one of the case studies. One of my students had just completed from his master's thesis. His study was related to climate change impact assessment on hydrology of Marshangdi River Basin in Nepal. Yeah, I have taken this case study to present to all of you for a few reasons. One is this is very new study conducted by my student just 2 months ago, and he used a new climate scenario called shared socioeconomic pathway. And also this river basin is very important river basin in Nepal because it has a lot of existing hydropower projects. And also there are few, hydropower projects under planning. And the third reason is I have been to this river basin many times, so I'm very familiar with the river network, the land use and land cover conditions, and also the hydropower projects located inside this basin. So this is the reason why I have, presented this case study here. Okay, let me briefly explain about this river basin called Marshangdi River Basin in Nepal, and it's very important to understand the characteristics of the basin before we proceed these kind of modeling studies. Yeah. So this Marshangdi River Basin in Nepal is located in the midwestern part of the Nepal, and it has catchment area of about 4,000 square kilometer. And very important is that almost 2,000 square kilometer of the area lies above the 4,000 meter above mean sea level. It means that the basin has a lot of snow and snow cover area, and these snow and snow cover are very important source of the water for this Marshangdi River Basin. So the elevation ranges from 349 to almost 8,000 meter above mean sea level. The average annual temperature and rainfall is given here. So the average annual rainfall is almost 1,700 millimeter, which is a pretty good amount of rainfall. And the annual discharge is about, sorry, so the annual discharge is about 218 cubic meter per second, which is at the Marshangdi River Basin outlet. As I mentioned that this river basin is very important in terms of the climate change vulnerability to the hydropower projects located inside this basin. Currently, there are 3 hydropower projects under operation, and about 16% of the total production for the hydroelectricity comes from these 3 hydropower projects. And there are 5 hydropower projects under planning, which is the installed capacity of more than 1,200 megawatt. And you can see the list of the existing or commissioned hydropower project and the hydropower projects under planning. So if you look at this, river basin map, you can see that these blue, the triangle, they are the commissioned or existing hydropower projects, and this red triangle are the proposed hydropower project. And the operation of the hydropower projects depends on the availability of the water in this main river and also the tributary river. So it's very important to assess what happens to the hydrology and water resources of this river basin to the climate change. So this is some of the photographs of the Marsangdi River basin. On the left hand side, this is the Marsangdi River view at the basin outlet. The middle one is the Marsangdi River in the upstream area of the basin, and the most right hand side is the Marsangdi River at the downstream of the basin. And you can see here, the river flow at the basin outlet. On the right hand side, you can see the average monthly rainfall in the basin. And in Nepal, the monsoon season starts from June to September. So you can see a very high amount of rainfall. In the below diagram, you can see the hydrograph of the basin in terms of the average monthly discharge, and corresponding to this rainfall, the discharge is also higher in June to September. So in this video, I imagine that this discharge is during the monsoon season. I can see quite big amount of flow. So it must be maybe during the July or August of the month. Okay, so this table shows what kind of data we have used for this climate change impact assessment on the hydrology and water resources. So as I mentioned that since the hydrological models are artificial representation of the hydrological processes of the river basin or watershed, and these hydrological processes depends on the several characteristics of the watershed, such as topography, land use, soil type, and so on. That's why we have to use these kind of data, like the topography, land use map, and soil map. They were obtained from these sources. The hydrometeorological data, we have used the temperature of 3 stations. We have used rainfall of 9 stations and discharge from 2 stations. And these are also at the daily resolution. And you can see here the duration of the data. This is 30 years of the duration. And these all data were obtained from the national source, which is from the Department of the Hydrology and Meteorology. And for the future climate data, we have used the data from 3 general circulation model or global climate model. And these data were obtained from this website of the Cordex project. And these data are also at the daily resolution. Um, these two maps are related to land use and land cover map of the basin, and the soil map of the basin. And on the left hand side, you can see the land use and land cover map of the basin. And these are the reclassified map. And you can see the majority of the land use is the forest land use. And there is also snow cover area of almost 13% on the northern part of this Marsangdi River basin. And this the snow cover or snow cover melting also contributes to the runoff into the several tributaries and also the major river of the Marsangdi River basin. On the right hand side, this is the soil map of the basin, and soil map, the majority of the soil is a loamy type in the basin. Okay, so this slide shows what kind of methods we have adopted to assess the climate change impact on the hydrology. And as I mentioned in the beginning, the modeling framework, this is a two-step process, and the first step is we have to generate the future climate data, how the temperature will change and how the other climate-related variables will change in the future. And we called it as a future climate projection. So in this particular study, we have used the climate data from three general circulation models. These are XSCM2, BCC CSM2MR, and ECR3. So these are the three general circulation models, and we use the climate data of these three general circulation models, both historical data and the future climate data. And there are several scenarios where these GCMs has already simulated, and these scenarios are from SSP1 2.6, SSP2 4.5, and SSP5 8.5. And the name of these scenarios I mentioned here. SSP1 is sustainability scenario, SSP2 is middle of the road scenario, and SSP5 is fossil fuel development scenario. So there are 5 SSPs data available, and the meaning of these SSPs are how the socio-economic development will take place in future, because the greenhouse gas emission depends on the socio-economic development and also the different kind of climate change mitigation and adaptation policies. So there might be different kind of scenarios that will generate different concentration of the greenhouse gases in the atmosphere in the future. So since we do not know how exactly the socio-economic development occurs in the future, so there are several scenarios proposed here, and based on that, there are different climate data are available. We also have the baseline data of the temperature and rainfall of 1982 to 2011. And as I mentioned that the data of the general circulation models cannot be used directly at the local level. So we have to translate these coarse resolution climate data into the local level by using method called downscaling or bias correction. So in this case, we have used the linear scaling approach of the bias correction to generate the future climate data into the 3 future period. One is called the near future, the second one is called the mid future, and the third one called the far future. And these time period is having 30 years. So we have the data of rainfall, average temperature, the maximum temperature, and minimum temperature of the daily resolution. And once we have this future climate data, we can feed these future climate data into the hydrological model, and we can simulate the how hydrology or hydrological processes changes in the future. So the second step is hydrological modeling, and in the hydrological modeling, we use this model called soil and water assessment tool, and this model is developed by USDA in collaboration with the Texas A&M University, and this is a physically based semi-distributed hydrological model which can simulate the hydrology, the water balance component, sediment yield, groundwater, and so on. You also have these, introduction of the SWOT model and how to use SWOT model in the subsequent session. So the SWOT model is calibrated and validated by using the discharge data of 1988 to 2011. So once we have these calibration and validated the SWOT model, we use this future climate data to see how the future discharge, snow melt, water yield, and some of the extreme hydrology changes in this river basin. Okay, I'll be presenting a few results from this case study. One is the future climate. In terms of the maximum temperature, we see that the maximum temperature will be increasing in the future in this basin. So in the x-axis you can see the time period, and y-axis you can see the annual average temperature, and until 2015 this is the baseline temperature, which is the historical observed temperature. Okay, and even you can see that this historical temperature is increasing in the basin, right? And after this you can see several lines, and these several lines are the temperature projected by 3 GCMs under different SSPs or shared socioeconomic pathways. And please just look at these bold line, and this bold line, the green line is the ensemble of the SSP1, the blue line is the ensemble of the SSP2, and the red line is the ensemble of the SSP5. Okay, so the ensemble are the average of the these 3 GCMs, and you can see that in all the future time period, the average maximum temperature is increasing. Okay, and the increment is different for different SSPs, right? For the SSP1, of course, the temperature is increasing, but increasing at the lesser rate than the SSP5. Okay, so here in the table, I summarize what is the change in the average maximum temperature in these 3 different time periods. Okay, for example, by the end of this century, the average maximum temperature will be increasing by 5.2 degrees centigrade with the scenario of SSP5, whereas it will be increased by 1.7 degrees centigrade under SSP1. So it means that there is a lesser increase of temperature under SSP1 and higher increase of temperature under SSP5. But you can see that the temperature is or expected to increase in all the future time period in this Marshangdi River basin. This is the result of the minimum temperature. The x-axis is the timeline, and y-axis is the annual average minimum temperature. Again, the dotted line shows the baseline temperature, or the historical observed temperature until 2015. And after that, you can see these are the lines related to the projected temperature in the future. And again here, the minimum temperature under all shared socioeconomic pathway scenarios are also increasing. So similar to maximum temperature, minimum temperature is also projected to increase by 5.3 degrees centigrade on by the end of 2100 under SSP 5. It will increase by 3 degrees centigrade under SSP 2 and 1.8 degrees centigrade under SSP 1. So both the minimum and maximum temperature are expected to increase in the Marshandi River Basin in the future. This slide shows the results of how the rainfall will be changing in the future because of the climate change. And again here, x-axis is the time period and y-axis is the annual average rainfall. And this dotted line is the baseline or historical observed rainfall. And after this, these all colored line are the ensemble of the bold color line are ensemble of these 3 GCMs. If you look at this table I have prepared here, so in all the future scenarios, in all the GCM, they are projecting that the rainfall is increasing in the future, or the Marshandi River Basin is getting wetter in the future. Okay, and then also the change in the rainfall is given here. For example, by the end of the century, in the Marshandi River Basin, the rainfall is projected to increase 731 millimeter annually compared to the average annual rainfall now. So it means that by the end of the century, the rainfall will be 1667 plus 731. So it's more than 2300 millimeter in 1 year, right? So the basin is expected to be wetter in the future in all the climate change scenario. So the temperature is getting warmer and the rainfall is also getting higher in the basin. But I try to analyze how the rainfall is going to change on a seasonal basis. Okay? So climate change will impact not only the average rainfall but also the the seasonal rainfall, intensity of rainfall, and so on. So in this graph, you can see how the rainfall is going to change in the pre-monsoon, monsoon, post-monsoon, and winter season in the basin. Okay, so this table shows the baseline rainfall in different season. Okay, and the graph shows the percentage change in the seasonal rainfall compared to the baseline period. So you can see that in all the seasons, the rainfall is going to increase in the future, except the winter season, right? So in the winter season, the rainfall is expected to decrease in the future. Yeah. Okay, so as I mentioned that in this case study, we used SWOT model to simulate the how climate change impact the hydrology and water resources. I will not explain in detail here because I see that there is a separate session for SWOT model. So basically, SWOT model is a continuous, physically based, semi-distributed hydrological model. And it has been widely used in several parts of the world to assess the impact of climate change, impact of land use and land cover change for water resources management studies. So it's quite popular model. And in this study also, we have used this SWOT model to simulate how the climate change, impacts the hydrology. Okay, so as I mentioned before, we calibrated and validated the SWOT model to see how the SWOT model captures the hydrological processes of this river basin. And the calibration and validation were performed at the basin outlet and also the upstream of the basin. And this hydrograph you can see here is observed and simulated discharge during the calibration and validation at the outlet of the basin. Okay, x-axis is the time and y-axis is the discharge, and you can see that the dotted lines are the observed discharge, whereas the colored line is the simulated discharge. I presented both calibration and validation hydrograph here. It is quite matching. So it means that the SWOT model is accurately simulate the hydrological processes in the river basin. The table here, it shows the some of the statistical indicator to see what is the closeness between the simulated flow and observed flow during the calibration and validation. So the statistical indicator are Nash-Sutcliffe efficiency, coefficient of determination, percentage bias in the volume, and also the ratio of the root mean square error to the standard deviation, right? So we have used these 4 indicators to see what is the performance of the SWOT model to simulate the flow. And you can see here, all of the statistical indicators values are quite high. NSC, if it is close to 1, we assume that the model perfectly simulates the flow. Again, R square, if it is close to 1, we also assume that the model simulates the flow very accurately. And the lesser the value of the P bias and RSR, the better the performance of the model. Okay, if the model has the P bias of the plus minus 15%, we say that the model is simulating the flow very well. Similarly, we calibrated and validated the model in the upstream of the basin, and you can also see here the comparison of the observed and simulated discharge during the calibration and validation phase. And in this table, you can see the value of the statistical indicator of NSC, R square, P bias, and RSR. So similar to downstream of the basin, upstream of the basin has also a very good performance of the SWOT model to simulate the flow. And we assume that this model is very good to use to simulate the climate change impact on the hydrology and water resources of the Marsangdi River basin. Okay, so I will present some of the results of climate change impact on the hydrology. And this slide is basically the change in the water balance and other component of the Marsangdi River basin in future. Okay? And this bar diagram shows the change in the precipitation, evapotranspiration, potential evapotranspiration, total water yield, and the change in the storage under 3 SSP scenario, which are SSP 1, SSP2 and SSP5. Okay, and these different colored bar diagram are the baseline period, which is the gray color, and the green color is the near future, and the blue is the mid future, and the red is the far future, right? So you can see that the precipitation in the future is expected to increase, okay, in all the SSPs. Similarly, total water yield is also expected to increase in the future, right? So for example, in SSP1, the baseline water yield is about 1,600 millimeter, but in the future, it might increase up to 2,500 millimeter. So this, the water yield is how much amount of water is going out of the watershed, right? So in terms of the surface flow plus groundwater flow, yeah, minus the transmission loss. So, in the particular, case study, we have estimated the water yield on a sub-basin wise. So I will show you that the spatial pattern of the change in the water yield in the subsequent slides. This is the change in the river discharge under climate change scenarios. On the left-hand side, you can see the average annual discharge in the baseline period and also in the future period, right? The x-axis is the timeline and y-axis is the average annual discharge. And inconsistent with the change in the rainfall or increase in the rainfall, the average discharge is also expected to increase in the future. Okay, so again, you can see that the bold, solid colored lines are, the average annual discharge in the future under three SSPs: SSP1, SSP2, and SSP3. SSP1 is green color, SSP2 is blue color, and SSP5 is red color. So the change in the annual discharge I have calculated and put it in the form of table here. So the change in the discharge is higher in the end of the century, right? So by the end of the century, the annual discharge will be increasing by 173 cubic meter per second, okay, compared to the baseline average. Similarly, in SSP1, the average annual discharge will be increasing by 121 cubic meter per second. So we analyzed how the river discharge is going to change in different seasons. These seasons are pre-monsoon, monsoon, post-monsoon, and winter. And you can see that different months are allocated for different seasons. And the percentage change in the river discharge is higher in post-monsoon and lesser in monsoon. Okay. So the post-monsoon, pre-monsoon, and winter season discharge increases are higher compared to the monsoon season discharge in this river basin. Okay, this map shows the snow melt under climate change. So I have prepared the spatial, variation of the change in the snow melt under the climate change scenario. And this darker, blue color are higher snow melt. So on the left-hand side, this is the snow melt in the baseline period, right? So the snow melt is higher in northern part of the basin, okay? And in future, we found that these snow melt is going to be increased in the northern part of the basin because of the snow cover area located in this northern part of the basin. So in all SSP, you can see that these blue and darker blue color these are the snow melt under climate change, and you can see the absolute change in the snow melt in the northern part is higher than the other part of the basin. Similarly, we also calculated how the water yield will change in different sub-basin to see the spatial variability of the water yield under climate change. And on the left hand side, this is the water yield in the baseline, okay, no climate change. And then the right hand side is the water yield under the climate change conditions under SSP1, SSP2, SSP5. And there are all the future period, right? Near future, mid future, and far future. And you can see the northern part and the central part of the sub-basins are having higher water yield compared to the other parts of the basin. Similarly, we calculated the change in the maximum and minimum discharge under climate change. So as I mentioned in the previous slides, that it's very important to understand the several components of the discharge, not only the average discharge, but also the maximum and minimum discharge. So the upper bar diagram shows the change in the maximum discharge, and the lower bar diagram is the change in the minimum discharge. And the table you can see here, these are the baseline maximum discharge and baseline minimum discharge. And the indicators of the maximum discharge and minimum discharge are 1 day maximum, 3 day maximum, 7 day maximum, 30 day maximum, and 90 day maximum. And you can see here in both of the indicator, maximum flow and minimum flow, these discharge will be increasing in the future. Okay, and this might have several consequences on the hydropower projects. As I mentioned in the beginning, that this basin has 3 commissioned hydropower projects, and also 5 hydropower projects are under planning. So of course, availability of water is increasing. Maybe it is beneficial to the hydropower project because they can produce more hydropower. At the same time, if the maximum flow are increasing, then it might bring floods into the basin, right? So if there are floods, then probably the several facilities of the hydropower projects are under risk. Maybe it will destroy the several facilities such as intake, probably the hydropower plants, dams. So there might be risk for the hydropower project, which can be analyzed, and several adaptation options can be proposed in this river basin. So these are the conclusions I want to make from this case study. So as you rightly notice that the basin is projected to be warmer and wetter in future, right? And the climate change will bring impact on the water balance. Water balance consists of rainfall, runoff, and other components like groundwater, lateral flow, and so on. So it's not only for the hydropower projects, perspective, but also for the other water resources management objectives. If the water balance changes, probably the planning has to be done accordingly. And the discharge, both average and extreme discharge, are projected to increase in the future, but it has both spatial and temporal variability, and it's very important to consider how these change in the discharge in terms of the average discharge, maximum and minimum discharge will impact the hydropower projects and hydropower facilities, hydropower production. So with this, I will stop here, and maybe we can also have some discussion on this, case study. Professor Ajay, yeah, if there are any questions, I'll be very happy to.
Yes, there are 3-4 questions in the chat box. You please go through it. Yes, one question is there from Rinki Dhruvansi. She is saying that she wanted to do the PhD under your guidance.
Yeah, I'll be very happy to accept you for PhD in AIT. So I suggest you to submit your application. Do you know the website of AIT and also website of WEM? Maybe I can quickly, give you the WEM website.
Yeah, that will be fine. And the last date when they should apply.
Yeah, actually there is no deadline for the
There's no
PhD application.
Right.
The PhD application is year-round, yeah. And we have 2 sessions. One is the January session, start from first week of January, and the other one is the August session. And we have the scholarships available for the August session. So if you are interested, you can apply now, and we can evaluate for the January intake as well as for the August intake. Yeah. So I have put this website.
Rinki, you please prepare a good statement of purpose and the research proposal, and that will be good. So all the best.
Yeah, Rinki, please send me email, and I will support you for your applications. Yeah.
Yeah, that's great. Is Vanita Pandey. She is asking that whether you did this study for sediment yield.
Yeah, Vanita, I did not do the sediment yield study in this study, but it is good that the Marsangdi River basin is mountainous basin, and probably climate change would bring impact on the soil erosion and sediment yield, and that will impact the hydropower project. And this is very important. And I was discussing with my former student that we should do a resiliency assessment of hydropower project under climate change. So it means that sediment yield study is very, very important.
Yeah.
Yeah, exactly. That's a good suggestion.
Yeah. Suman Dev Burman is asking, sir, in this river basin, only one gauge station. So how to validate upstream discharge data?
Suman, if you remember correctly, I presented the calibration and validation in 2 locations. One is at the basin outlet, and another is in the upstream. So both of the right, right.
Upstream will take care of that.
Yes, right, right.
Then Divya is asking, sir, why did you consider only 3 GCM? Why you have considered 3 GCM only?
Okay, Divya, that's very good question. So there are 2 questions here. I can see one is, why did you consider 3 GCMs? And the another question is, for bias correction, have you adopted linear method for both rainfall and temperature? Okay, yes. In the bias correction, yeah, we used the linear scaling for both temperature and rainfall. So the question of the selection of the 3 GCMs is very, very important. Yeah, in fact, we have to use as many number of GCMs as possible, because there are a lot of uncertainties in climate change projection, right? So probably many of the GCMs, they can simulate the climate differently, right? And we do not know which GCMs will simulate the climate accurately. So in that case, it's always better to have these multiple GCMs, to project the future climate scenarios, and then use those multiple GCMs, the future climate scenario, for the climate change impact assessment studies. Maybe one GCM can simulate wet conditions accurately, and another GCM can simulate the dry conditions accurately, right? So because different GCMs, they have different kind of structure. They use different kind of equations, although the boundary conditions and initial conditions are same, okay? Because they are developed from different modeling centers, and the performance of these GCMs probably vary from one GCM to another GCM. So that's why we use more number of GCMs. But in this particular study, we used only 3, again, because of the limitation of the time. Yeah, I have several students, they are using 20 or 30 GCMs also, basically for the PhD studies. So my suggestion is, the larger the number of GCMs, the better is the results, or better is the assessment results.
Yes, one more question was there from that Amit Raj. Sir, how to assess that artificial impact of climate change on water resources? How to assess artificial impact of climate change? Yeah.
Right. Amit, I think the artificial impact, you mean the impact caused by the human activities, right?
Yes, sir.
Anthropogenic impact, right?
Okay.
Yes, sir.
Yeah, that's good. That's very good question. So there are several, anthropogenic activities that will impact the hydrology and water resources, right? Okay, so I read your question again, but looks like your question is related to how to assess artificial impact of climate change on water resources. Maybe I misunderstood. Do you want to say that anthropogenic impact of
Amit, you can unmute yourself
Yes,
if you're talking.
I did mean the same, sir. Anthropogenic impact.
I see. It's not the climate change, right? Yeah, the recent climate change is due to the anthropogenic activity, right? It's not the natural. The rate of the increase in the temperature is very, very high because of the anthropogenic, greenhouse gas emission. So that's the different part. But I think your question is related to how to estimate the anthropogenic impact on the hydrology and water resources. So there are several activities, right? One is the construction of the dams and reservoir. The another is the conversion of the land use and land cover. For example, conversion of forest area into agriculture area, right? So, in the model, we are using the hydrological model or any other kind of water resources systems model, right? So in those models, you can, create some scenarios to change the, land use and land cover, right? In SWOT, for example, you can change the land use and land cover from forest to agriculture, from forest to, urban area. So if you are using this SCS curve number method, and you can change the curve number that represents the change from the forest to agriculture, forest to urban, And when you simulate, that gives you how the land use and land cover change impact the hydrology. Okay. Similarly, in the SWOT, there are several, water storage module or reservoir module. So when you develop the SWOT model or set up the SWOT model in the area where there is no reservoir, you put the reservoir in the SWOT model, and you simulate the SWOT model, and you can see what is the impact of construction of the reservoir of different sizes in the area. So that's how we simulate how the anthropogenic activities impact the hydrology and water resources. Is that clear, Amit?
Yes, sir. Thank you, sir.
Okay.
Okay.
Okay, I see that another question from Bala Sundaram, right? Is there any possibility of analysis temporal changes in a particular areas by using any model? Yeah, I think SWOT model is a continuous process-based model, Bala. So SWOT model gives you the daily, changes in the flow, right? So it means that if you have the daily changes in the flow, you can do analysis of the temporal changes, no? And it has the spatial unit, like HRUs and also the sub-basin. So you have one sub-basin, and then you have a daily flow of 100 years, and then you can easily do this temporal change, yeah? Okay.
One more question is from Banita Pandit.
Yeah, Banita, using multiple GCM also increases complexity of projection because different GCMs are based on different assumption and boundary conditions. Is it advisable to adopt this approach? Yes, that's true. That's true that multiple GCM increases the complexity of projection. That's true. But at the same time, you have to also understand, there are uncertainties in climate change projection, right? So it's always better to use multiple GCMs to address those kind of uncertainty. Yeah, it's difficult, complex, but I think there is, if you have to prescribe the policy recommendations to the policymaker and planners, I think it's better to use as many number of GCMs as possible. Okay, Professor Ajay, I think I will go to.
Yes, Adi, we have a specific sessions on climate SWOT model and then hands-on SWOT model.
Right.
So
right.
your query will be replied there only. I think that many of the candidates have appreciated your lecture, Professor Srest.
Right. Right.
And, let us conclude then. That one question that we can take? Feedback form sent, please. Yes, feedback form will be made available from AICTE, and you have to give on the website. Let me talk to them.
Sir, may I ask my question? I have one question.
Khushbu, yes, please.
Yes. Sir, actually, I have run the SWOT model for Bangalore, that is a complete urban area, and there are no stream gauges available for validation. So, if you could, any of you experts could highlight, like I'm suffering from this problem, like where I'm not able to validate my results. I'm using proxy indicators, using empirical equations, but is there any other way people or like experts are using to validate SWOT model in an ungauged catchment, which is the case of Bangalore city? Thank you.
Yeah, so if I understand your question, you are using this SWOT model to simulate the runoff in the urban area in the Bangalore, right? And you do not have the stream flow data, right?
Yes, sir.
Yeah. Okay. The essence of the physically based hydrological model is that um, we use as less number of parameters as possible, because these are the physically based model, right? So there are several equations which are based on the physics, right? So rainfall runoff processes, groundwater recharge processes, evaporation and evapotranspiration processes. So it is based on the physical process. So the essence of development of this kind of models are we use as less number of parameters or data as possible. But at the same time, if you do not have these runoff to calibrate the model, one of the ways is to calibrate the other component of the water balance. Okay, so you can see how well the SWOT model can simulate the evapotranspiration or evaporation, right? So nowadays it's getting popular that we also calibrate the model by using other water balance components like evapotranspiration. Okay, so if there is no any other alternative, I think using this evapotranspiration parameter to calibrate the model also is valid. Yeah.
Okay, sir.
I think there is no more question. Shruti Verma has appreciated. Okay, fine.
Okay,
Professor Shrestha.
Yeah.
Yes, we'll conclude here.
Okay. Yeah. Yeah. So I really enjoy the presentation and also the question and answer session. I think all the participants, they are very impressive questions. And they are very important questions. And I'll be very happy to be in touch with all of you. If you have any questions and also the other suggestions you want to take, like to pursue your master's or PhD, I'll be very happy to help you. And Professor Ajay, thank you very much for inviting me to this faculty development program. We communicate in email, but it's very nice to see you face to face. I'll be very happy to explore the collaboration opportunity.
Yes, we have a wonderful session, and this is our honor that you got involved with us, and we hope that we will make some programs where you will be invited again.
Yeah,
and
thank you.
Yes, really, this is a wonderful group. I saw all the questions. They are not learners; they have worked on it. And
Right.
many MTech and PhD students are there. And
Right.
that's why we have kept the hands-on SWOT and HECRAS and web model, where we will go very slowly. And some of the research scholars of the department, they have been engaged, because that hands-on will be delivered by them only. We will not be able to do that.
Yeah, that's
so
right.
I think, yes, many more things will come, and let us hope to get educated on this water resource modeling. Thank you very much, sir.
Yeah, thank you, Professor Ajay, and thank you, everyone.